Okay, I think we'll get going. It's given it's just gone past 10. So, welcome to this Archer 2 course on GPU programming with HIP. We're going to discuss a number of topics today related to programming GPUs and try and take you from an introduction of why we might want to use a GPU for programming all the way through to how to actually program it and do that, look a little bit at performance and ways you can do that. The final exercise of this is to write a simple solver. Apologies, there's some mechanical noise in my office lane. Just checking to the other moderators, is that bleeding through to the audio? There's some drilling in the office.
Just a little bit, but it's not. I mean, the voice is clear and it's okay, so it's not a problem.
Okay, fantastic. So given that Juan's just spoken up, so me and Juan. So I'm James Richings. I'm a architect here at EPCC. Juan is also an architect here at EPCC, and we will be sharing the delivery of this course material. So I'll be taking this morning and tomorrow morning, and Juan will be taking the afternoons. As we sent around an email, unfortunately, due to some service maintenance, we will have had to move the Wednesday slot to another time. I just want to check that everyone here has a chance to respond to that request for an additional time for the course or for the third day. I think when we said the 31st in the end, was that correct?
Yeah, it seems that most people vote 31st, like a Monday next week. So it's probably that if in case that it doesn't work for you, please let us know now. But I think yeah, will be Monday next week. I will copy the link of the form in case that someone wants to. But yeah, please answer the form as soon as possible.
Yeah.
Or just
if anyone has
mention in the chat if if Monday 31st. But yeah, it seems that would be Monday 31st.
Okay. Yeah, so please message in the chat if you have any issues around this, and we can discuss with you solutions. There's a couple of ways we can work around specific dates if needed. Okay, on top of, so let me just get my screen shared. So actually, let me just do this first. On top of that, we have a couple of links I will share. So this first link is the link to the course page, which enables you to get to the course materials at the bottom, and which are located at GitHub here. And we'll be downloading and using these materials throughout the course. The other link it provides you is access to our chat system. So while we have the chat on this monitor, this screen, we also have an Etherpad. So I'm going to give everyone a little bit of a headache for a moment while I just share my screen. Actually, I can just do it by tab, can't I? So we have this Etherpad system, and we use this to enable to take notes. So it highlights about who the question's from, and what we encourage people to do is if you have questions that we're not picking up in chats because the chat will keep scrolling, we can ask you to put them into here, and we can come back to them at a time when we can pause. The danger is that if lots of chat starts happening on the online session, we may miss things. So if you think we've missed something you've asked and we've not got to it, if you paste it in this Etherpad, which you can find the link to, I think I'll just paste it into the session. Yeah, I have at the bottom there. We will come back and review this from time to time to make sure we're covering off any questions you have. It also allows a shared space for us to sort of keep a record of questions asked and answered, so that other people have the similar question. I think they can look at this back through and see the sort of thing that, that people were querying. Okay. So now I can share without giving everyone a headache. The course materials, I think it is that one, yeah, are on this GitHub. We basically will go through each of these sections in order throughout the 2 days, and most of them have some form of exercise file and a README about how to do that in them. We will use this in order to develop and build on the previous sessions. Each of the exercises usually builds on the previous one and provides some form of solution before it adds additional complexity to the example. That way, we're enabling you guys to sort of learn and not be held up by an issue in a piece of code. So you don't require to use the same solution all the way through. If you want to keep developing the single piece of code, you can, but if you get stuck, you can look at the next example to get a hint about what's going on. Okay, that's that. Finally, scheduling. So let me just share my PowerPoint. Okay, they're coming through. Good. Okay, so this course material is shared under a Creative Commons license, so can work in collaboration with other people. We have partners that deliver the Archer 2 service alongside EPCC. The service is funded by UKRI, specifically ECSRC and NERC users. Obviously, we're at the University of Edinburgh, and the hardware vendor that we work with to provide Archer 2 is HPE. So a couple of bits of sort of preparation work. You should have all received a link to sign up to a Archer 2 project. You should have hopefully had a chance to log into Safe and set up an account. If anyone hasn't done this, please message in the chat now, and myself or Wan will be able to talk you through the steps. But I think I saw a lot of people had already signed up, so hopefully that won't be necessary. The advantage of signing up to the training account, if you have existing access, is we have certain reservations set up and time allocated, so you're not going to eat out of other budgets. But essentially, the setup should be the same for any other Archer 2 account. The GPU nodes on Archer 2 are not currently allocated out or charged, as it's a development platform. You will need to make sure you've got an SSH key and your MFA token to log into Archer 2. And if you have any issues, please let us know. But if everyone could just log in quickly and test this is all working for them and they can get a success, please do that now, as we rely on this for the rest of the course. So if I could ask everyone just to do that and put a message in the chat when that's been successful, that would be great. Just take 5 minutes now to do that. Right, where was I? So, right, yeah, I've kind of covered this already, but let's just go through some of the key learning outcomes here. So there's a 3-day course, which we're going to have 2 days and then another day next Monday. We're going to cover the HIP and CUDA programming model. The main learning outcomes are to have you guys have a broad understanding of why GPUs can offer an advantage over CPUs, to understand how to move data between host and device, between host being the CPU and device being the GPU. Now to write kernels, to run code on the accelerator on a GPU, to understand occupancy and why it's important to drive performance on a GPU, an introduction to the various types of memory spaces available on a GPU, because there's 3 or 4 and they offer different performance and benefits and potential drawbacks, or more add complication, and give you some practical experience of implementing a few simple kernels. And doing this, we're looking at both what's called streams and graphs, which we'll come on to later. Okay, so kind of covered the topics, but we're going to talk about the performance model of graphics processors first. So that's what the first presentation this morning. We're then going to talk about the specific programming model of CUDA/HIP. We'll then have a section on memory management, and we'll start to get you to do some actual coding at that point. At that point, I think we're just going to take lunch. We'll then afterwards talk about executing a kernel, and we'll get you looking at ways to implement this in a variety of ways, and implementing some of the stuff we've discussed around the programming model with a simple kernel. After that, the last thing we want to do today is talk about some performance considerations and look at how we can drive performance when programming GPUs. Tomorrow morning, we'll look at managed memory and shared memory, and then constant memory. So these are the different memory spaces for GPUs. And then tomorrow afternoon, we'll look at streams. We'll try to review the examples as we go. And you cannot see the sharing content. Okay. I'm going to stop sharing and share again. Is everyone else able to see what I am sharing? If you are not, then I will try something different. Is that working? Right, I'm currently showing a slide called Topics. Is everyone able to see that? Okay. Okay, do you want to try restarting your browser? I personally use Chrome. I don't know, Juan, whether you have any recommendations for browsers that work with this well, with using Collaborate.
I remember in the past I used Firefox and other. It's recommended Chrome, but others should work. I had the issue before, and the problem is, yeah, restarting the browser, it works.
Okay, so okay, that seems to be working now. Okay, I'll get back. Okay, so these are the topics we're going to discuss. And this is the rough breakdown. So we'll aim to have regular breaks so that I'm not talking at you too much. Usually once an hour we'll have 15 minutes to kind of just have a comfort break. We'll aim to have lunch at 12 to 1. We'll try and keep that pretty set. And if we have to move stuff around slightly, like I usually end up going a little bit faster in the mornings because some of the introductory content we get through a little bit quicker. And in the afternoons, it's better to have a bit more time to go through some of the detailed practical exercises, whether it's around. And we may not be doing so much interaction, but we're here to answer any questions. So especially, for example, executing a kernel and looking at some of the performance considerations, we'll have lots of time to do that and spend the time debugging or dealing with issues and things like that. If people finish that early, especially towards the end of the day on the final exercise and feel like they're complete, that's okay to head off a little bit early. And what we'll do tomorrow morning is we'll review that exercise at the beginning and discuss some of the outcomes from it. Okay. And yeah, we'll spend a decent amount of time trying to do that to make sure that everyone's on the same page and you can understand the learning outcomes from those bits. So maybe like we're building a lot of time for that, but I think it's important that you see those in detail, especially when we're discussing performance, because we're going to want to drill down to some profiling of that too. Okay, I've sent links of the course materials and some more details into the chat already. On these slides, there is a number of useful links that you can take a look at. Specifically, the user docs on Archer 2 here under user guide is very useful. I can't show that easily, but I'm just going to copy it into the chat. This has a lot of information about compiling and running on Arch 2. The HIP documentation is quite useful, but be aware that you're on the right version. I've actually linked the wrong one here. I think we are on version 5.2.3, not latest. It should broadly, for the stuff we're doing, not matter, but if there's technical details you're interested in, make sure you pick up the right version. I'm also linking the CUDA docs. You may be asking why. It's because HIP tends to mimic CUDA pretty closely. The functionality isn't usually implemented to the same level of detail, but it is there. It is often implementing a similar API. There are two GTC talks. This is NVIDIA's sort of annual general conference that they run. It's just had its most recent iteration, so I should update this with some other interesting talks from there. These particular sessions are very interesting. I'm pretty sure these are the ones that I have by Stephen Jones. He's an excellent speaker discussing about how CUDA has been designed, but more importantly, why the API is designed the way for GPU type architectures. So if you want to do a little bit of reading around, and I want to understand a little bit more detail about what the principles that have gone into designing the API and how you should think about programming GPUs more generally, those are two excellent talks, and I strongly recommend you take a look at them if you have 5 minutes. Okay. So first of all, we're going to spend a little bit of time motivating some of the discussion for today and why we care about graphics processors and why they might offer us an advantage. So a very simple model of a computer is this diagram on the right. I have some processor that performs operations on some data. That data is stored in memory, and I move the data in and the results get moved out, or I move data in, process and produce a result, and then I copy that data back out to keep hold of it for later, for some later processing. Okay, I have data movement and I have operations I do on the data. There are a number of factors which can be taken into consideration when we're thinking about performance. If we want to improve performance, we could do more operations more quickly. So that's clock speed. I increase the rate of issuing of instructions by the processor. I do more things in a given amount of time. I'm therefore more performant. Alternatively, I could be limited by the time it takes me to go get a piece of data. So if I've only got to get a very tiny piece of data, where I just need a single scalar value and it's stored on my main memory, somewhere in my RAM, the time it takes me to go grab a single data item is latency bound. It's the time for the request, not the transfer of a large amount of data. Therefore, minimizing my latency will be important. And what we'll come to see is memory latency and how we deal with that is very different between CPUs and GPUs. Memory bandwidth is the amount of data we can transfer in a unit of time. So as in my previous example, I just had a single scalar. The unit of data is very small. Therefore, I should be able to copy that in a single step. Therefore, latency, the time it takes me to send the first bit of data, is the limitation. If I am trying to transfer a file or an image or something much larger, the ability to transfer that data as a stream is limited by the memory bandwidth, because I'll have to chunk that up in some way. And that's going to potentially limit my performance. And what we'll see is that most applications in practice are memory bandwidth bound. So how I get my data into my processor, I can issue instructions incredibly fast. Can I get information to those instructions quickly enough to make sure that I am doing useful work as often as I can? That is much more around why GPUs are designed to operate versus CPUs. They're trying to minimize the memory bandwidth and try to hide latency in order to drive application performance. Okay, and then also parallelism. So the other thing we'll see is that CPUs have tried to parallelize by increasing the number of fundamental units, the fundamental sort of core or processor that is implemented in the CPU. That's been duplicated a lot in order to do things simultaneously. Can I drive that performance even further with additional parallelism? The answer is yes, in GPUs, we really take that to the extreme. Okay, so I'm just going to go through each one of these now in a bit more detail. So you've probably all seen this plot a lot before, but it's a very, very important plot, and it's even more important when we come to think about why GPUs have become a predominant piece of hardware, especially in HPC over the last 5 to 10 years. So processor clock speed determines the fundamental rate of processing instructions, and then that therefore limits the rate we can process data. Historically, CPU clock speeds have been CPU performance has been related to increases in clock speed, and you saw this right up to about the 2000s, 2010-ish. And what you saw is around that time, and I realize some people here may be a bit more junior, there was a sudden emergence of the multi-core processor, especially on local machines, right? You're used to up until a point in the 2000s, you had the Pentium 4, and it went at sort of 4 gigahertz, and it was a single processor. And what you do is you switch in different instructions would time share the processor, and it would have one core, go very quickly, but it would swap in and out and change context and do context switching a lot. What you started to see after the mid-2000s is that you couldn't really drive higher and higher frequencies anymore, because what you were doing is you were increasing the power usage and the efficiency, and therefore the heat in your processor, and you couldn't push that any higher, and it wasn't efficient to push it any higher. So actually what you started to do was, instead of driving clock frequencies up, you would drive the number of logical cores up, and then you'd parallelize, you'd have different cores take on different processes, and they could run simultaneously. And if you've got a Windows application running and of sort of Word or whatever, and you've got a calculator and you've got PowerPoint open, well, they can each happily sit on a different processor. They don't require resources, there's no contention there, they can run simultaneously, and you as a user of a local system can quite happily do what you needed to do efficiently with a multi-core setup. What we often see in HPC land is that we barely got something like 3 gigahertz clock speeds. What we like to stay at is around 2 gigahertz. That's because the scale of this problem increases massively. The amount of power we start to use, if you imagine Archer 2, it's using up to order 2 megawatts of power every single second of every single day. And that's running at about 2 gigahertz, 2.25 gigahertz clock speed for every CPU, and there's 5,000 nodes. So by the time every single node uses a couple of hundred watts of power in order to drive application work, and that's a lot of power we need to get out of the system to maintain its performance. Otherwise, CPUs like to thermally throttle their performance if they're getting too warm. There's not really an opportunity or advantage to going much higher clock speed. So this isn't really a direction we continue to head in. And what you've seen instead is the number of core count has dramatically increased. So basically, without some fundamental breakthrough in the underlying technology, we don't expect clock frequencies to increase to be a way we can drive additional performance in hardware in the foreseeable future. So we have to go at this in some other way. The other limitation of potentially performance is memory latency. So as I was saying, the memory latency is a serious concern. It's going to be the focus of why GPUs are designed the way they are. It may take 100 or 1,000 clock cycles from some form of standing start to retrieve a piece of data from memory to the processor, where it can then be operated on in some register. Okay, so then we can actually do something useful with it. A CPU attempts to mitigate this problem by having caches. Memory that is closer to the processor and thereby reduces the time to access the data. We have many caches in a hierarchy. The closer to the processor, the smaller the cache in terms of its size, but the faster the access speed, but also the increase in the cost of the memory. Fast memory costs a lot of money, and what you do is you layer this so you have small but close and large but further away from the processing cores themselves. Right. Just so we're going to do something a bit practical and I don't just talk at you for 45 minutes. Can everyone log into Archer 2 if you haven't already, and just run the lscpu command on the login node. What I want you to do is I want you to find the different size of the caches, and I want you to paste them into the chat when you found them. Okay, great. So lots of people are getting ahead of that. Fantastic. Hi, Jen. What is the instance? What do you mean by the instance here? Oh, sorry. In this, I think it's the number of copies of this you have across the CPU. So I imagine that because the number of cores you have on one of these Archer 2 CPUs is quite high. We'll come on to that in a second when we talk about parallelism. It's relating to the number of copies of these caches that you have. So what we'll see is that each core has you'll have an L1D and an L1I cache and an L2 per core, and then you'll have a shared version of the L3, which is 32. So that's going to be what? There's 64 cores per socket, and you have 2 sockets per node. So you're going to have 4 cores per L3 cache. I think that's right. Okay, I think everyone's kind of got their own in there. So yeah, you have a hierarchy of caches, and they are aiming to try and smooth out this memory latency problem in order so that when you access data, the CPU can do something smart and say, right, I'm expecting a certain amount of data in the upcoming instructions. Let me put that in the closer cache, and then I can do something clever to access it. Yeah, 4 cores per L3 cache. Okay, great. I can do mathematics on the spot. Good. Right. Your other constraint, memory bandwidth. Right. CPUs generally have commodity DRAM, dynamic random access memory. The speeds of commercial RAM is around 100 gigabytes per second. Sorry, the overall size is around 100 gigabytes. The exact size that's provided in a particular system is really a driver of cost. RAM is very expensive these days, and therefore actually the cost of the RAM is a significant cost of your modern CPU node or your modern GPU node or your local laptop. It varies in cost depending on generation and speed. You do not always need latest and greatest to have a very efficient system. So if you are interested in designing your own computers, think about whether you really need crazy expensive RAM. Is that really what's going to benefit what you're doing locally on the machine? In HPC, however, this is a serious consideration for us, and we do need to spend money on efficient, high bandwidth memory, as this often limits our application speed. Yeah, so our maximum memory bandwidth is usually on the order of 100 gigabits per second for commodity hardware. Many of your applications are not limited by the rate in which you can issue instructions. They are limited by the ability to get the data to the instructions quickly enough. And what I'm showing on the right here is a roofline plot. So what we have in red is peak performance, which is the horizontal line. That's just the number of instructions we can issue to the processor. By the processor, and that's the theoretical flops limit of what our processor could do, running at 2 gigahertz, and it can do, I don't know, what, floating point addition or some other operation, right? And along the diagonal, we have this memory bandwidth bound, and that's saying how quickly can I get the data to this processor, and that limits me. What you can then do is measure the arithmetic intent intensity against the available flops you can get for your particular application, see whether you're memory bandwidth bound or you're compute bound. So if you're underneath this diagonal line to the left of this sort of green dash, vertical green dash, you're memory bandwidth bound, and to the right, you're compute bound. It's quite rare to be compute bound. You're usually bound by your memory bandwidth, the ability to get data. So that said, when we come to think about GPUs, we want a way to try and maximize our ability to get data into our compute in order to minimize the effect of this boundary, or at least raise this boundary up a bit further so we can attain more performance. Okay, finally, parallelism. So once we hit a limit of the clock speed that we can do on a particular processor, we can try adding more processing units, multiple cores. Many CPUs now either have local laptops, usually sort of order of 10 to 20 cores, if they're very nice. On HPC hardware, we're talking 64 cores per socket, or on a node, it's 128. If you look at NVIDIA's Grace offering, that's 72 cores per chip. And it starts to get up even higher as you go into future generations. Again, this is limited by what can you physically fit on the hardware, on the particular die, how big is your chip, and what are the power and energy constraints of your particular platform. This allows you to run multiple, to use these cores to do operations in a particular scientific application and to parallelize your work and allow you to do more work per clock cycle because you've got more units doing stuff. Okay, so same again, if people can just look at the LSCPU output and get a sense for yourselves what the core count is on Archer 2, and I want you just to consider whether what it's showing you makes sense. So yeah, run out that same command you just had. It's going to give you a number of CPUs. What's the number it gives you? Why might that number be incorrect? And I want you to also run the same command on your local system and compare it to what the output for your local machine is. And if someone can post to the chat when they're done about why they think there's a difference in potentially the reported value by LSCPU, that'd be great. Oh yes, Alice Topper was next. I will show that in a second. Yeah, I will update these slides to show that as well. Another tool for the interested in HWLock can produce very nice graphical outputs. I think actually that is Alice Topper, isn't it? It's supported by HWLock. You can get lovely diagrams showing you all of this stuff in nice graphical outputs, but there's also an ASCII output, so it's easy to run on a local machine in a terminal. Okay, is anyone able to give me an answer for the number of cores on an Archer 2 node? Just paste in the chat when you've got something sensible. Great, okay. So I'm just going to share my terminal and just go through and show you what Juan was talking about as well in terms of Alice Topper, because that's a very good thing to show. Right. Can you see a window where I'm typing in into a terminal? And is it far too small? Yeah, okay, great. You say good. Right. Okay, so I'm on Arch 2. Cool. So so if I just run hostname, I'm on login node 2. CPU, right? So we get a lot of information out of here. We have 2 sockets. We have 64 cores per socket, but we get reported 256 CPUs. And when you look at the breakdown, you have what's called NUMA regions. We'll come on to it in a little second. You can see there's a bunch of splitting over here as well. The key thing here to remember is that this is reporting hyperthreads. So basically trying to share a single CPU to do 2 different, a physical core, and it's generating 2 virtual CPUs effectively, enabling you to sort of time share a particular piece of hardware. So just be wary of that if people aren't aware of that. The key thing to say is this is the maximum you're going to do if you're going to, in terms of number of cores and the simultaneous threads on a CPU is 256, and we'll come and compare that later to what we can see on a GPU. The other thing to note, for those of you who aren't aware, is you have what's called non-uniform memory access regions on these CPUs, and there's 8 of them, and you can see here this is how it splits the threads of those hyperthreads over the different NUMA regions. All this really means is about closeness of memory to a particular set of cores. Okay, so that's that. Just want you to get just to recap a few things about the CPU, which we have, and just go through a few elements for understanding what is there. So we can also do LSTOPPER to look at cache hierarchy. As you can see, this is kind of a complicated output, but effectively what it's doing is telling you which group it's in. So it's these NUMA regions. There's 8 of them. This is the 5th one. Okay. Pick any one of them, and we can look at and see there's a certain amount of RAM, there's a certain amount of L3 cache, and there's a certain amount of L2 cache, and these are split between different processes and numbers. Okay, and then you've got the L1 caches as before, and you get core numbers. So that's quite useful to see that split out. There's also graphical outputs of that are quite nice. If you want to generate a pretty diagram, HWLog has lots of information on how to do that and how to generate the nice graphics if you want to produce pretty pictures of what the underlying architecture is delivering. You can also do this for GPUs, GPU nodes as well, and produce information about where the GPUs are connected to, which can become important when you get on to looking at how GPU nodes are constructed at sort of larger scales. Okay, right. I'm just going to go back to sharing my slides. Okay, so right, we've recapped the sort of fundamentals of the CPU, and now we're going to talk about finally about graphics processors. Right, where have they come from? Why are we starting to use GPUs to program and game performance? Originally, this was generated by the previous commercial interest of NVIDIA and other GPU providers, which was gamers. There are many core processors par excellence, so basically they have got thousands of cores available to you in order to really scale up that parallelism. So while the CPU can get to a couple of hundred if we use hyperthreading, GPU is on the order of thousands of threads. So our ability to really push towards high levels of parallelism is much increased if we use GPU. They're designed of exactly the same components fundamentally as a CPU. The particular design choices of the individual components and the way they've been optimized will be different, but the fundamentals of there must be some form of cache, there must be some form of processor. The complexity of that processor may well be different, but the fundamentals are the same. We must be able to move data from memory into the processor to do operations. That's the same. How we organize and batch up that memory and the operations, that changes. That's what could drive extra performance. So in terms of the physics, we've got to worry about power, we've got to worry about cooling. They're subject to the same design choices, and they've been resolved in this particular way. And originally this was around dealing with large arrays of pixels on a screen, which was effectively a big 2D grid or a 2D matrix. And they can all be operated on independently because every single pixel can determine its basically red, green, blue color value independently. Okay, that was nice and trivially parallelizable. Clock speeds of GPUs are typically lower than CPUs. So what you've actually done is sacrificed a bit of clock speed. Usually they're between about 1 and 2 gigahertz. They usually say at the moment sitting around 1.4 to 1.8. Mainly because of the issue of getting enough power and cooling the heat generated by them, because you've got so many more of them, has generally gotten a bit lower. Memory latency is still a problem, but the mechanism used to mitigate this is now different. What you can describe CPUs as latency minimizing, and you can think of GPUs as latency avoiding. What it's doing is having the ability to switch tasks very, very efficiently between different blocks of work, which we'll come on to in a minute, and therefore hiding the idle time. So while one block of work is going, I need to go fetch some information from memory somewhere, another block is ready to execute, and therefore you reduce the effect of the latency, but it's still there. And what we'll see this in terms of performance is that the best way to get performance with GPUs is to give a lot of work so that the GPU can stream through this work and effectively hide latency as it goes and gets different bits of data by switching stuff in and out as it requires. Okay. So, what else about GPUs? GPUs generally include very high bandwidth memory. They themselves have a relatively small capacity. This is all of the tens of gigabytes. You're starting to get to just hitting 100 gigabytes in the latest generation of GPUs. I think Hoppers is something like 96 gig, or maybe there's a SKU that's 144 gig. It's really not the 256 or 512 on the high memory node you'd expect on a CPU node from a Arch 2, for example. But the bandwidth is much larger. So you're going to spend a lot of money on memory bandwidth of sort of order of 1,000 gigabytes per second, opposed to sort of order of 100. So you're trading off the total capacity for additional speed. This gives you a much better balance between data supply and data processing. For when you're trying to sort of render screens, you can do lots of things in parallel. You want to be able to get the data very quickly. So when you are sat there going, I need to go get a section of something to render, I can go and get that section quickly and try to minimize the memory bandwidth. I've still got some latency to go get that data from memory, but once I've decided what the block is, the whole block should transfer relatively quickly, and I can hide that transfer time by switching context again relatively fast between independent blocks of work. So the key thing here is GPUs tend to have thousands of cores. Okay. So I'm going to now try and describe some nomenclature around GPUs, and I will try and provide you a bit of a conversion table between stuff you may have heard from NVIDIA and the way that AMD likes to refer to their setup. We're going to use AMD hardware for the work with HIP, but I will try and use their jargon. But be aware that you may see this be interchanged, and I may mess up and use the wrong one. The one I will usually mess up is calling things blocks opposed to work groups, but we'll come on to that in a sec. Okay, cores on an AMD CPU are organized into units referred to as compute units. Each CU or compute unit contains several smaller processors called stream processors. These processors are responsible for carrying out the mathematical operations. They're doing the actual arithmetic work required for tasks such as rendering graphics, encoding video, performing scientific calculations, or whatever else you want to do that's supported by the instruction set. Each of the AMD Instinct MI210 accelerators present in Arch 2, they boast 104 compute units each. Each compute unit has 64 streaming processors. So in total, you have 6,656 streaming processors that can work at the same time on each of the GPUs. on each node in Archer 2, you have multiple GPUs. So you can see you've increased the ability to do your operations in parallel by a huge leap over that 256 cores we had on the CPU. Each of the CPU cores are going to be more complex and can deal with have other mechanisms in which to work share, parallelize, things like that, that won't be quite enabled by the same core on the GPU. But we've got so much more of them, and we've got this enhanced ability to get data from the memory to them quicker, that we can gain a massive advantage. There's more detail on the AMD website around this particular technology that you can look up. And then the sort of jargony bit, so in AMD parlance, compute units is the word we'll use, or the name we'll use for a particular block of streaming processes. In NVIDIA language, a compute unit is a stream multiprocessor, and a stream processor is a CUDA core, which really doesn't make things easier because two things are using stream and two things are using processor, and they're for different things. I will try and keep to compute units and stream processors throughout these lectures. The bit I'm likely to mess up, but try to keep consistent, is the next bit. We will talk about wavefronts in AMD's language, or warps in NVIDIA's language. So these are groups of threads executing the same instructions. And this is a really important concept. So we'll have wavefronts and warps are groups of threads doing the instructions. And finally, we will have work groups in AMD parlance, or blocks in NVIDIA's words, for data we're going to operate on. So we're going to have work groups to operate on a certain set of data, or we're going to have blocks to work on to do some set of operations. Okay. So just to reinforce the idea that the GPU is fundamentally made up of the same thing, this is a slide on an NVIDIA A100 GPU, and the compute unit is sort of made up of, so a particular A100, for example, has 2048 threads per stream multiprocessor. It has, it can do 32 blocks of work per stream multiprocessor. It has 32 threads per work versus AMD has 64 per wavefront. It can have, and this is important, 4 of the warps active at any one time. So while we have a lot of threads, only a certain subset can be active doing useful work. And there's certain limits of cache and cores to do certain operations. So the 64 cores available per stream multiprocessor to do floating point operations, or there's only 32 to do double precision operations. Clock speed, as I said earlier, is about 1.4 gigahertz. And you have other bandwidth considerations. They only have a certain level of cache, but they're organized in fundamentally the same sort of fundamental blocks as we saw with the CPU. They're just slightly different design choices into them. For MI200 series GPUs on the AMD side, they're designed in a very similar way. You have some number of compute units, and each compute unit has a number of these streaming streaming processes in the center. You can dispatch work to them, and each streaming process is going to take an individual item of work. The instructions are shared across all of the different streaming processes within a particular wavefront. And this is what's really driving this performance. Whereas on a CPU, every core is going to have a different instruction potentially. It can deal with branching, it can deal with making decisions, and they don't have to individually be in lockstep. On a GPU, groups of cores work together with the same instruction on different data in order to perform operations, and that's driving performance. Okay. We'll come back to that picture a lot. I realized I'm slightly running over for this session, so I wanted to get you guys a break and stop talking at you for a bit. We also have this picture of host and device to try and bring this all together. So we have a CPU on the host side with order tens of cores, 128 cores on the Archer 2, for example. I'm pretty sure on our MI210 nodes, we only have something on the order of tens. We have some memory, capacity order of 100 gigabytes, and bandwidth order of 100 gigabytes. We have some transfer between, okay, let's talk about the device side. We have a GPU which has order of thousands of cores and memory bandwidth of thousands of gigabits per second, but we have a very small capacity order of tens of gigabytes. I then have a limited transfer speed between a host and device, between the CPU memory and the GPU memory. This is the order of tens of gigabytes. In more modern GPUs, there's been a lot of effort to increase the speed of this. So if you come across a Grace Hopper or a MI300A, they're very closely connected CPU and GPU, and there's a design decision to try and increase the bandwidth of these speeds. You're getting an order of hundreds of gigabytes a second transfer between the two. They are often presented as unified memory. That is, I think that's a misnomer. I think much prefer if they would call it uniform memory. You access it in a uniform way. You don't have to worry about that too much, but it will have an impact on your performance. So what you want to do to gain performance is minimize the amount of data you transfer on and off the GPU. You want to get the data you need over to the GPU, and you want to work on it lots and then move it back later in your application. So the CPU basically becomes an orchestration tool for the GPU. Is going to do as much of the work as possible, and you want to keep work over there, and you want to do much of the work as you possibly can. Okay, so the GPUs we're going to be using, the GPU nodes we're going to be using are MI210s. We talked a little bit about them. We have 4 GPU nodes on Archer 2. This is a test and development system as part of the service. Obviously, this is not much scale, but it does allow you to do a little bit of development and have some access. Each node has 4 GPUs, these MI210 GPUs themselves, and there is a single CPU per node. You will need to submit a Slurm job to get access to the GPUs. There are no GPUs on the login nodes, so you won't be able to run any commands to probe the structure of the GPUs locally, and there's documentation in the Archer user docs with lots of detail about the nodes themselves. Okay, so we have some scheduling configuration to how to actually do the submission to these nodes and get access. We need to submit a job from the Archer 2 login nodes, and in the exercise we provide scripts about how to do this. So a lot of this should be set up for you, but if you want to look around this for your own interest, or you want to use this later, or design your own scripts for submitting to the queue, there's documentation. But the key thing here is there's 2 quality of services. There's a GPU partition, and there's either a shared or exclusive quality of service you can apply to. The idea of shared is so that a node is shared between multiple people and you get access to a GPU. Allows you to share the node with other users and allows to get most people on as much as possible. We'll use this for the majority of our work during the course. Alternatively, there's an exclusive mode where you get the whole GPU node to yourself. So there's a limit on the number of nodes of 2 so that other people can run on the system at the same time. Yeah, so when we allocate, we ask for a request for resource, we need to request minus number of GPUs in our Slurm options. We also need to think about how to minus gres and specify one's GPU and the number of GPUs we want. We don't specify the number of CPU cores or the amount of memory. It is allocated as a fraction of the total based on the number of GPUs you've requested. So the host resources are tied to the GPUs in a sense. So there's 8 CPU cores and 128 gigabytes of memory per GPU. So these nodes, I think they have this Milan CPUs. They have 32 cores and half a terabyte of RAM. Once you've allocated your resource in the Slurm script, and you can use srun to run multiple tasks, and this is going to call an MPI underneath for you. Okay, I provide this slide just to give some references of various different hardware of different providers. So I'll just talk to this a little bit. I think this is still up to date and current. So NVIDIA, you have, for example, there's been many generations of GPUs, but the V100s were sort of the order of 2017, 2018 timescales, and that's what we have on our Cirrus service, tier 2, that's coming towards the end of its life at the moment. Just around the beginning of the pandemic, you have the A100 GPUs. These are available on the DirectTursa system, and we have a number of them in our EIDF cluster. And then more modern, we have H100 Hopper GPUs, and they are provided via the EIDF GPU service as well here at EPCC. Grace Hopper is sort of one of the latest and greatest things. It's a year or so old now, but still very modern and beginning to be deployed at large scale across the HPC sphere. These are the things, this diagram on the bottom right here, that couple the CPU and the GPU very closely and try to deal with this bandwidth between host and device and couple it very closely. However, where the memory you allocate resides will have different access speeds because the quality of the RAM you've got on the CPU or GPU differs, basically. And you still have an imbalance. So the CPU has much more RAM, but it's slower. The GPU has much faster RAM, but there's less of it. On the AMD side, we have MI210s, which are available on Archer 2. And then you're looking at things like MI250 and MI250X. So MI250X is what is in Frontier, the first HPC service to deliver an exascale, exaflop or reach exascale of performance. They're effectively sort of two tiles of each of our GPUs in Archer 2, linked together in a complicated way. If you have access to LUMI in Finland, I also have MI250Xs. And more recently, there's been releases the MI300A and the MI300X. The MI300A has CPUs and GPUs embedded on the same chip, and the MI300X is a pure GPU, similar to what we're going to see in the MI210s, MI250Xs, and all the services. Additionally, Intel, well, we're not going to speak about them because they have a slightly different programming model. They use something called SYCL. They are on the Aurora HPC service that's also reached exascale in the US. They have had some troubled time delivering the service. It's been delayed from its original in-service date due to some of the challenges of delivering high-performance GPUs. And the Intel offerings is the Max series GPU. In the UK context, Dawn has some of these available to you. If you want access to that, then go speak to our Cambridge collaborators and colleagues, sorry. For UK access to Grace Hopper, I believe Bede has a number of these available on a test service, or it is the Isambard AI service has Grace Hopper nodes. The other thing I should say to round out my just sort of brief overview of exascale services, El Capitan in the US has MI300A GPUs, and they deliver an exaflop of performance, and that was announced. They are almost well above 1 exaflop now at Lawrence Livermore National Lab, and that is gone into service recently. So AMD has delivered much more to the exascale HPC community in terms of what's been bought and delivered, mainly as a cost consideration. I think there, I'm sure NVIDIA could do it, but it's quite a costly GPU platform to be able to purchase, given the demand from the AI community. Okay, so GPU, we're mainly talking about, so that's a bit of an overview of some of the hardware that's out there at the moment, some of the hardware you may come into contact with. We're going to talk about particular kernel approaches to programming GPUs. That's the HIP programming model, and it's very similar to the CUDA programming model. There are other approaches to this as well. So you could look at OpenMP offload or OpenACC for directives types approach. If you're used to OpenMP, might provide you a way to access GPU performance much quicker if you've got a already OpenMP'd code, although that is not as simple as it may seem. Some of the decisions and designs choices you may have made for CPUs will not be appropriate for GPUs when you're using directives. And what you're really training off here is this kind of this big diagram I've got here is sort of portability of your code against level of control of the hardware you're using. So if I want to use the greatest and latest versions of CUDA features, if I'm programming CUDA, I'm going to get them first, and I'm probably going to have the best control over them. But if I want something that's more portable, then maybe directives or one of these other portability frameworks is going to provide me more of that. And it's how much this is abstracted away and how much other compilers are going to do some of this work for me about how to organize the work that's delivered onto the GPUs. Portability frameworks, we have sort of three systems designed. They're all C++ based, so people who are interested in Fortran maybe much prefer OpenMP Offload because there's better support there. But Cocos, Raja, and SYCL. SYCL is an offering that's developed by a couple of community, well, one community version, and there's one commercial version by Intel. A team called CoPlay developed this based after ERAS in Edinburgh. And that allows you to both program the Intel Macs, but also does allow you to target AMD and NVIDIA GPUs also, and also allows you to target CPUs too. Raja and Cocos are two libraries that came out of the Exascale Computing Project in the delivery of exascale services in the US, and are another option if you're interested in programming GPUs. Again, they're C++ based and provide you portability in what you're programming. So if you're expecting the type of hardware you're going to target and you're going to write a new application, maybe they're a good option to you. If you've got an existing application, you may want, or you want particular control over something, directives or kernel approaches may be better. I'll just flash this up briefly. So there's lots of different languages and there's level of support. This is a nice paper from Andreas Hurton, providing some analysis of the level of support for different languages from the different approaches to programming GPUs. Right. I have run over slightly there. I would like to take a 5-minute break and let you all also have a brief break. Are there any questions before we do that? We will come on to discuss this. So, so the question from Jenna is, are CPU and GPU memory both in a universal address space? They, as of a compute capability, I think everything you most likely see from NVIDIA and others will be in a universal address space. It's practically what's happening underneath there is some translation union, which is taking, if you've got an x86 processor on the CPU side, a lot of the GPUs are ARM derivative constructs underneath. One of the reasons you may have seen a few years ago, NVIDIA was very keen in buying ARM was because a lot of the underlying technology, hardware technology, is licensed from them. You will need some form of translation. And therefore, while you have a mechanism for accessing memory, you will have to do this either explicitly or certificate is being managed, and that will have some performance impact. The advantage of being completely universal and having exactly the same hardware, exactly how Grace Hoppers are designed, the CPU and GPU have exactly the same memory design, and that allows uniform access from either one, can address and access directly each other's memory space. There is a lot of confusion around the nomenclature around what is uniform and what is universal addressing. And I have to go back and remind myself of exactly what this was done at different stages. My advice is usually do not assume you will get the same performance from accessing either space, and you will need to consider how you're accessing that data if it's not in the local region of memory. So you will need to provide some form of pointer to that device memory. You will need to explicitly copy memory over, and we'll come to that in a session earlier this afternoon. Okay, we're going to take a quick 5-minute break for people to go to have a comfort break, because I've spoken to you for an hour and 20 minutes. At 25 past, we'll come back and I will discuss some of the information around the programming model before we get to lunch. Okay, start again at 25 past. Okay. Hopefully everyone's just had a couple of minutes to grab a cup of tea or take a little break. So, we're now going to discuss some bits about the fundamentals of the programming model. We've kind of discussed in the last session a fair amount around what's the design decisions around GPU hardware, how does that differ to CPU hardware, what are the key drivers of performance in applications, how are they limited, how are the design decisions different, driving different performance characteristics in GPUs. Now we understand a little bit about the elements of a GPU and how it's different. How do we now control that? So the application programmer doesn't want to worry about the exact decomposition of cores, compute units, and the hardware in general. We want a nice, easy-to-use abstraction which deals with all that underneath, where we can control it if we want to be able to get performance. But most of the time, we want to leave that for a compiler or the runtime to deal with. So we need a way of describing our problems into a hierarchical organization of threads work to do. So we want to decompose our work into threads. So for example, if we have some form of one-dimensional problem, e.g. we have an array, we're going to assign individual elements to different threads. So if I have some array we're going to do an operation on, the first element in the array is now assigned to thread 0. Element 1 is assigned to thread 1. Okay, and we can continue that up to a certain size. Some array x. That allows us to do each of those operations simultaneously, as long as they're all independent. Now, if I'm combining information in element 0 and element 1, they're not independent, so they can't be assigned to different threads. But as long as I'm doing independent work, so that, for example, the addition of two vectors, find x and y, thread 0 could take an element of x, take the 0th element of x and the 0th element of the y and add them together, and we could do this same operation, they're all doing it in lockstep, they're all doing addition over two vectors, and that would be okay. Now, when we discussed our nomenclature and our jargon for the organization of work on GPUs, if I have some long vector, I want to split this up into groups, so into work groups, or in NVIDIA language, this is a block. It's a collection of work items or threads. It's scheduled to run on a compute unit, or in NVIDIA terms, a streaming multiprocessor. And in the one-dimensional picture, we may have something like this, where block 0 has a number of threads, 0 to however long, and then block 1 has a series of threads, 0 to however long. Each of these blocks can be executed, and if they stall because they need to get some memory from somewhere, they can be switched out for another block. And we can maintain occupancy, that's the use of the hardware on the GPU, to a high level by making sure we're able to switch in different blocks of work at different times. As we have issues with going to get memory, we have a delay due to memory latency or some other form of fetch that causes us to have to stop execution of a particular block. So a wavefront is a subset of a work group. It's designed to execute in a single SIMD or SIMT, single instruction, multiple thread unit. So my particular block of work could be very large. It could be 256 threads worth of operation, and a particular wavefront could do 64 of them at a time. Okay. A wavefront are mapped onto compute units for execution by the hardware scheduler. So my blocks say this is a block of work, go do it. You can do 64 bits of it at a time, go schedule that, and come back when you're done and the whole block's complete. And if I have lots of blocks, then I can use lots of different compute units, and I can use up my entire GPU, and therefore drive high occupancy. So as a developer, you typically select a number of wavefronts or work groups based on the size of the problem. So how you divide that up so that you end up with balance of work. This expands itself into 2 dimensions. So this is the example I gave earlier where we had some from when we're doing graphics processing, so the origin of the use of GPUs, where we want to do relatively simple calculations over a large array, a 2-dimensional array for some form of screen. I can expand this notion of arrangement of work groups or blocks and refer to it as a grid. I have a grid of work groups that I assign to some compute unit, and then a set of threads within that work together as a wavefront and execute simultaneously on the hardware within a compute unit. They can be switched out for different groups of threads as and when needed, when there's a data request or some other thing that could stall us. That's going to minimize latency by hiding it under this a large amount of work we have to do, and then making sure there's always something available to do is the job of the programmer, and that can drive very high performance. And as we scale up the amount of work we need to do, that means we can occupy thousands of threads on our GPUs, and that gives us a massive performance advantage over our CPU counterparts, potentially. In CUDA and HIP, we could extend this 2-dimensional picture into a 3-dimensional picture relatively straightforwardly. We're not going to do that because it gets a little bit complicated with how to visualize. But what you can start to see is that you can organize your blocks into the z-axis effectively as well. So here we just got the x and y direction. So I've mentioned the word HIP a few times. So it stands for Heterogeneous Compute Interface for Portability. It's developed by AMD, the developer of the GPUs we're going to be using. It's a runtime API and a kernel language. So it's implemented in C++. This tool enables developers to create applications that are portable across AMD GPUs, but also target CUDA devices alike. That's the portability bit. The runtime is what's going to run and schedule work on the GPU device and make sure that work is moved and data is moved back and forth between the CPU and the GPU. The kernel language bit is the bit we are going to write our code in order to enable certain effects on that device or moving data between the device and the host. HIP has 2 distinct types of source code, host code and device code. Host code is essentially the CPU executes something the CPU executes on the host. This is typically C++ syntax, incorporates standard features, has an entry point for execution in the main function, utilizes the HIP API within it. Host codes facilitates tasks such as generating device buffers, managing data transfers between host and device, initiating execution of device kernels, device code. The device, typically the GPU, executes device code. This utilizes a C-like syntax where kernels are launched onto the device. Instructions from the host are queued into streams of execution on the device. We'll come on to streams later in the course, but you always execute on a stream, but unless you specify otherwise, there is a default stream that exists to execute on. And this may be a smart thing to do or not a smart thing to do, depending on what you're trying to achieve. So this is a serialized thread of execution. So this in terms of scheduling on the device. Okay, compilation can get a little bit tricky. For HIP, we have HIPCC is a compiler driver utility that calls the AMD LLVM compiler, AMD Clang, or MVCC if we're targeting NVIDIA GPUs to compile HIP code. Okay, HIPCC is included in the AMD ROCm software stack. HIP-CC compiles both HIP code for GPU execution and non-HIP code for CPU execution. So basically, it does two passes. It calls the AMD LLVM compiler, so AMD Clang or AMD Clang++, where it's needed. Other compilers can be used for non-HIP code, and object files can be linked in set in different ways as well, if you so choose. These compilers are all available on Archer 2, and we'll talk a little bit about the modules we need to load in a minute. So to use HIP-CC, so you can use HIP-CC -help for a list of options to compile the code. The main thing we're going to focus on is things like HIP-CC -x HIP code, where the -x HIP operation instructs HIP-CC to interpret the code as HIP-specific code, therefore we're targeting AMD devices. You can make different decisions there. If you want to see what the HIP-CC passes into the compiler, you can use the -verbose option. This is very valuable to really understand what it's unpacking underneath. On Archer 2 specifically, we have a number of different programming environments and compilers available that are able to compile code for the HIP device. What we've got at the top is a list of all the, you can find these two tables in the documentation on the Archer 2 docs around GPUs. So we have things like the AMD compilers, Cray compilers, GNU compilers, GNU, AMD hybrid, Cray, AMD hybrid, okay? They don't all support compilation for the GPUs for HIP. So specifically, we need to program AMD really, or program with Cray can be used for this as well. There's a bit more support for OpenMP offload. If you're interested in that, there's limited support for OpenACC. And what this kind of shows you is that while GPU programming is getting mature, the level of implementation support by compiler writers is not ubiquitous. It's not like a new C++ or C standard or Fortran standard. The amount of maybe Fortran's a bad example here, but the time it's taking to implement this in the compilers is relatively slow, and you have a limited number of options for support. So your ability to get around bugs by trying different compilers or looking at different performance optimizations is much more limited in the GPU space than it is in the CPU space. Okay, different generations of hardware have different compute capabilities in terms of their supported features. What this means, you have to specify what you're targeting when you do this. So we have to explicitly pass HIP-CC and offload Arch. This offload Arch is GFX90A, so you can see where I've gone ahead. Sorry, I'm trying to highlight with my cursor. Here, depending on the exact hardware you're targeting, you'll need to choose a different particular label for this. You have exactly the same thing in NVIDIA land as well. There you pick a particular generation code or gen code. So for us, we are of the MI200 series, so all the MI200s share the same gen code. So this is GFX90A. If we're using earlier higher in the MI100 series, the MI50 series, we'd use something different. So just be wary if you're on different hardware platforms or you have access to AMD GPUs in a different location, you may want to make sure that you're using the correct generation code. There's also have limitations around portability if you to take binaries from one system to the next. Okay. So a bit about portability. I've mentioned this briefly earlier, but it's important for people who either have existing GPU codes on multiple ports, maybe something you're trying to learn about how to do as part of this course. So CUDA has been developed for a much longer period of time than HIP has been, so it's about 2005 for CUDA. AMD is rather late to this party, and which develops HIP, and it sort of shadows CUDA in terms of its functionality. So for example, as C++ called, so CUDA malloc is simply replaced by HIP malloc with the same signature. So that allows HIP code to be compiled for NVIDIA GPUs by the inclusion of an appropriate wrapper to substitute the relevant CUDA API routines. Not all the latest CUDA functionality is implemented in HIP at any given time. Obviously, as things are implemented in CUDA, HIP has to come later and provide support for their own for AMD GPUs potentially. And what we'll see especially is that while some of the APIs are available, does it give you the performance benefit underneath. So graphs is a particular example where is it actually doing anything useful? So graphs is a way to combine certain kernels and reduce the overhead, the launching of the kernel overhead costs. And is it actually doing that in practice for the AMD GPUs, or is it only really enabled for under the CUDA code? There are other things like that you may see when you try to do comparisons or try to just natively convert from CUDA to HIP. So another useful tool can be something called Hipify. Given there seems to be a relatively simple mapping between CUDA and HIP routines, it'd be good if there was a way to convert this, and there is one provided by the AMD developers called Hipify. There's a guide to porting on the AMD docs, which you can use. And what it allows you to do is just scan a particular directory for files containing CUDA code, and how much of that code can be automatically Hipified. It basically just does the replacement for you and provides some information about that process. It does an okay job. Anecdotally, we have some people from HP who work with us who've done this a bit and say it does a good first pass, but does require users to patch up bugs and do debugging, and maybe there's been mismatches in certain versions of the APIs. So you can use it, but don't expect it to work perfectly. Okay, so really what we're talking about here is that the goal of the program is to describe the problem and the programming of the GPU in an abstraction in terms of grids, blocks, and threads. We'll come on to that in more detail when we look at the kernel example later. The hardware is then free to schedule the work within each of those blocks to specific threads in a compute unit, and it is allowed to switch those out because they're deemed to be independent. Each of the threads are deemed to be independent. That allows you to scale up the amount of work and hide some of the latency issues you can see when trying to access data. And that therefore requires for best performance to really have a lot of work to do so that these blocks can execute, finish, and immediately move on to the next piece or switch them out. So you need a large amount of data to work on to take advantage of these thousands of threads you now have to execute on the GPU. This provides a basis for scalable parallelism for this type of GPU architecture. The very latest HIP programming guide can be found in the ROCm docs under HIP latest. For the currently installed version of Arch 2, we are on 5.2.3. So if you're finding a particular thing as you're looking at the docs during the course to try and debug something or understand something better, you will need to take a look at this particular version to be accurate to what is installed in terms of the runtime and the compilers on Arch 2. Okay, so we have 15 minutes before lunch. Do we have any questions around that section of the material before I move on to talk about some of the last little bit before the first exercise today? I feel like I could hear a message, but I didn't exactly see one. I don't have any messages in the Etherpad, so I will assume silent means agreement and move forward. Just going to try closing that tab and reopening in case I've missed something. Okay. If someone has a raised hand, I can't see it, so please go ahead and speak if you want to ask something. Okay. Sorry, I just had a weird ping, maybe think someone's also saying. Right. So the first thing we'll talk about is, so what I'm going to do is briefly go through the slides around programming and memory management, and then people can look at this as they want to during the next session. So if I can everyone see? That's the annoying thing I wanted to avoid, but now we can at least know we're all seeing the right thing. Okay, so we've already talked about this host and device model a little bit. The first thing we're going to discuss and try and program is to talk about memory movement between host and device, and really try and understand the concept of moving data between one space, memory space, and another. Okay, so we have the host side and we have the device side. Just even a little bit more, so that makes a bit more sense. And what we're doing here is we need to have a mechanism for allocating data on the GPU from the CPU. So we need the CPU to issue an instruction saying, give me some data on the device, the GPU. We need a way to move data between the two locations. And we need to be able to so we're going to do some operations. We're not going to do anything to begin with. That will be a kernel call. We'll talk about that after lunch. And then we need a way to move data back once we're done. Okay. So what we want to include in order to write standard code is we need to include the HIP runtime, which is usually relevant for codes we're going to compile with HIPCC. But there's also a subset of the API, which is which is just the interface, which doesn't need to be compiled with HIPCC. So you can just have the HIP runtime API if you want that instead. What we're going to talk about is memory management. So data is accessed by kernels must be reside in device memory. Sometimes also referred to as device global memory or just global memory. I don't like for people referring it to as global memory because I think that becomes ambiguous and a bit confusing, because if you had some form of managed or shared memory between the host and device, you might think of global memory as being access to both. So it'll be device memory or device global memory. I'll try and refer to this as. The different ways of managing or moving data between the host and device. Broadly, we can do explicit allocations and explicit copies, which we're going to talk about here. Or you can use managed memory. And that effectively says, I'm going to allocate some memory and some space, and you're going to put it somewhere. And let the runtime manage where the memory is going to be active and cached on the GPU or the CPU side, depending on when operations are happening. That means the complexity to program it is much simpler, but you are potentially limited in performance, because one of our major bottlenecks, if we go to this diagram, is this link of doing the copy. This is rather slow. This is order of tens of gigabytes. The GPU to its memory is order of thousands of gigabytes, and the CPU to its memory is order of 100 gigabytes, and this GPU to CPU memory is order of tens. It's getting better. Things like the Grasshopper nodes are providing a lot more performance there, but it's still not very fast. So we need to limit the amount of copying we're doing. So if we allow the managed memory space to do the copying for us, we may end up with a performance limitation, because it's going to decide when to do the copying, opposed to being, and it may do that more often than we want it to if it tries to move stuff out of the way. So we may want to control that explicitly ourselves to minimize it. Okay. So how do we do memory allocation? So this is all code that executes on the host. And we're going to, first of all, allocate some pointer of data, which is going to be data on the device. It's basically saying, I want to know where on the device I'm going to allocate some memory. And I need to have a pointer to that location so I can pass that around and provide access to that to other, to transfer data to it, or pass it into kernels and things like this. So I have a HIP malloc call, and I pass in this pointer, dereferenced, and I provide the address of this to HIP malloc, and I provide the size of the data I want to do. So I've got some array, n array of doubles. I'm going to pass this in. I'm going to perform some work, and later, before the end of my program, I need to free this data. Okay, this is one of the dangers of these type of interfaces. This is C style, not C++. I've not got some nice object which, when it gets destroyed, deletes, calls a destructor and deletes this memory for me. I need to remember as the programmer to free the memory. So be careful about this, to make sure you remember to include these type of frees. Such pointers are host pointers to device memory. So the host owns the pointer. It contains an address of memory on the device. They have a value, but they cannot be dereferenced by the host. That's a programmer error because the memory address relates to space on the device and the host cannot access it. Each of these calls returns some form of error, and we will return to error handling at the bottom of this section. Okay. So, memory movement. I'll just do this, it's easier. Usually there's a zoom level, I guess it looks a bit better, but that's fine. Okay, so once we have established that there is a pointer to some location on the device, stored in data, and that location has some size, I now need the mechanism for moving data from the host to the device and the device to the host. That's the call kip mem copy. And the way this should always be read is I am copying memory from a device to its destination from its source, and this is the size of the copy, and this is the direction of copy. Okay, there's more than just simple host device or device to host. I could have device to device, or I could have something asynchronous things happening here. We won't discuss this right now, but there are other options than just two. Hence why this is a little bit, you've got a full name here to enumerate what this should do. But again, this is the destination, this is the source of the data, this is the size of the data to be copied over. I then do some operations on the device, and then I want to copy the result back in the same location. So say it's just a double, in our example, it's going to be a doubling. So I want to pass the doubled result back. Then I'm going to copy from the destination, it's going to be the host, the source is going to be on the device, it's the same size, and now notice that the name has changed, it's device to host, opposed to before we had host to device. These are blocking calls, they will not return until the data has been stored in GPU memory or an error has occurred, so basically it will block any other transactions happening on this data. And again, they return error codes we'll need to handle. The signature is provided here. So you've got this name here is a mem copy kind. It provides a direction. Given that you're dealing with asynchronous operations, so the device is not controlled directly, and if something happens with the mem query that throws an error, that error is potentially happening silently on the device side, and you will not see it inside the host thread of execution. We need to be very careful about about error handling. So most HIP API routines return an error code of type HIP error underscore T. It's important to check the return values against a HIP success. So if they're not successful, you then need to do something. The error code can be interrogated by and provide some meaningful information via a couple of helper functions. So there's HIP get error name and HIP get error string. So the name just what's the name of the error string is the description of the error. In practice, we've provided in our examples a nice little macro that basically grabs the call of the function and checks the error, checks the return of the error, and then prints some information around it if an error is caught that's not equal to HIP success. Sorry, so response is not returned as not HIP success. We've provided this macro for you in the example. It's in particular important to check these API calls to detect problems in this HIP context. What I would advise is little checking macros like this for your own codes as I collect them and try and keep them around in a useful place. I remember them when I have to write HIP code so that I can have them on hand and very quickly look at them as and when they're needed. So I've talked to you a lot so far and we're now up to lunchtime, so we're going to take a break here for an hour. When we return, we're going to spend half an hour, not 20 minutes, looking at this particular exercise in this directory. So this is the dscale hip.cpp. And the simple template is as follows. We are going to declare and allocate some device memory. We're going to copy it to the host, some space from host to the device. We're going to copy it unaltered back from the device to the host to a different location, h out. So h in is our input. We have some place in device we're going to set up. We're going to copy back to an output, and we're going to remember to release the resources on the device. Once we do this, this test you need to compile it and run it on a GPU node on Archer 2, and that will perform a little test to check if you've done this correctly and print you a message to check if all the values are correct in the expected output. I just want to show you that macro real quickly. So we've got some error handling function which is defined, and all our macro does, is define and assert. We're going to wrap all our calls in a hip assert, and it just calls this error handling function. The definition of this error handling function is at the bottom. When the error handling function is called, it tests whether it returns a failure and calls hip success. It checks if it's hip success. If it's not hip success, let's print some information. We run hip get error name, we run hip get error string, and then we exit, okay, from the code. Using standard exit. This allows us to make sure that we pick up the error and exit from the program in an appropriate way. Okay, thank you for listening to this morning. I know this morning has been a lot of me talking at you. This afternoon is going to be a lot more hands-on and practical work, where we're going to look at particular examples around first doing this memory copying, then we're going to look at executing kernels. Juan's going to take you through this afternoon, but I will be in the chat for any questions you have. Before we break for lunch, are there any other questions around the course, setting up this particular bit of material, anything else I can help answer? Okay, if there's no questions immediately, we'll start again at 1 o'clock. Feel free to take a look at the exercise over lunch if you want to, but we will spend half an hour when we come back just going through it, doing it. We're going to start slowly and try and be methodical and give you guys time to do the exercises. So if this is, for people maybe who've looked at some of this stuff before, this may seem relatively straightforward. It's important that we just go through some bit of foundation because we're going to build on top of this later. Okay, see you all at 1 o'clock. Thank you very much for spending your time with us this morning.